the point I made about going to these conferences is that many people in these various conferences since even the 1960s have been calling for some needs for the limits to growth or something like that, or else that the limits to growth will be upon us by resource constraints. And these ideas were very much alive when I was a graduate student in the late 1960s. And during that time, it was very much part of the curriculum at, for example, the University of North Carolina. We had a whole week of people coming in and talking about environmental problems and so forth. And there was this limits to growth study, and that a lot of people looked at that, and I was very interested in it. But then the price of oil came down, and we understand why that was. For biophysical reasons, the price of oil came down, and people didn't care anymore. The economists thought they'd won the argument, which they in fact had not. And then people forgot about it until the price of oil goes up again. Now, all of a sudden, I tell my mother I've become a micro-celebrity. You put in Charles Hall Energy into Google, and you get usually between 5 and 15 million hits, depending on, I don't know what happens at Google. But and as far as I've been able to stand going on those things, about half of them are to this Charles Hall and Space Aliens, that's not me. And Charles Hall and Aluminum, that's not me, but all the ones on energy, in fact. So somebody's paying attention. A lot of people, I think, are paying attention, but they're scattered. They're here and there, and it's not mainstream. And it's not endorsed in any way by ecological economics, or certainly by any conventional economics. How do conventional economics deal with me? They don't. They don't want this discussion. I'm ready to go into any economics department anywhere in the world and give the same talk. And I have great confidence in what I do, because as somebody trained in physics and chemistry and biology and geology and all of the real, I should be careful, the natural sciences, you know, we know how to do science. And any science that you do has to be consistent with the laws of thermodynamics. It has to be based on, it has to have the right boundaries. It has to ask and test hypotheses. Conventional economics doesn't do any of those things. So I'm not going to go in there and argue as an economist. I wouldn't. I'd go in there and argue as somebody who understands very well natural sciences, which they are not constrained by. Even though real economies are, economists frequently are not. We teach 1 million young people a year in the United States economics as if it were something real, where to some large degree, in my opinion, it's a series of fairy tales. And I'm willing to debate any economist on that. Investment. Energy return on an investment is the energy that you get back from investing and getting energy. Let me start with a biological example. A cheetah, if it's trying to race down a gazelle, has got to get more energy from the chase, 90% of which are unsuccessful, than she gets from the energy invested in the cheetah. And the cheetah uses so much energy that they overheat and have to stop running at some point, because they're really using a lot of energy. So, but not only that, she has to get enough energy to produce her kittens, to lactate, to do all of the things, train her young, and all of those things. And in the natural world, any organism, a tree, a fish in the stream, and I've studied fish a lot, any of these organisms that use more energy than they gain are going to go extinct. It's a kind of iron law of natural selection. We asked this question, I did with Cutler Cleveland, who was an undergraduate student of mine back in 1981. We asked this question about looking for oil in the United States, and found that the energy cost of drilling for oil was going up while the energy return was going down. Now, if you want to say drill in the Alaska Wildlife Refuge where we know there's oil, that makes sense. And if you want to go, well, let's go and drill in some brand new place that we don't have any information, but simply increasing our drilling rate in the way that we normally do when the price of oil goes up does not bring in more oil, and it greatly reduces the energy return on investment. At least historically, that's been very much the case in the United States and in other countries as well. The political statement, drill baby drill, doesn't have any validity, at least historically, because when we've drilled more, we haven't found more oil, and we've used more energy in doing that drilling, because you can only find oil by collecting information over time from the fields that you've already drilled to get information about where is the next good place to drill. Yes, they are really quite different. Originally, the idea of ecological economics was wherever, any place that ecology and economics overlapped. But in fact, this is not how it's evolved, and another of our presenters today made a very good case about how ecological economics has basically been just conventional economics applied to natural ecosystems, natural processes, and prices, just pricing a parrot or something like that is part of what it has become. So biophysical economics is an attempt, first of all, accepts that conventional economics is highly flawed, and especially highly flawed to anybody who's trained in the natural sciences and in the scientific method. For example, in beginning economic textbooks, you don't get the basic ideas given as hypotheses that are then tested. In fact, you hardly find that anywhere, occasionally, but hardly find it anywhere. And that's the essence of real science, is use the scientific method. And the basic model in conventional, what we call neoclassical economics, breaks the laws of thermodynamics and has the wrong boundaries. So any of those things would destroy you in conventional natural sciences. We'd say, well, that's simply not true. So biophysical economics is an attempt to develop economics from the perspective of being consistent with the real laws of nature. It doesn't exclude social science. Good social science is certainly more than welcome in what we do. But let me just ask you this question. If you think about what does economics mean to you personally, not economics in the university, but economics to you, most people, after thinking a bit, will say, well, food on the table, a roof over their head, perhaps access to transportation or something like that. But what it really is, it's about stuff. It's about the physical, biological, and physical world. And if that's what economics is about, why should economics be a social science? It's very peculiar. In fact, it used to not be. Back in 1750, the physiocrats focused on land as production, and the classical economists, Adam Smith and David Ricardo, who I talked about today, focused very much on labor, and then eventually the neoclassical economists don't focus very much on production, but if they do, they talk about capital. But if you think about it from a biophysical perspective, each of those is about the main source of, main input of energy to the economies of the time. Land captured solar energy. Labor, when people were concentrated in factories, was the physical activity of a laborer, would make whatever the goods and services were. And capital is a means of using energy, which has enormously expanded, in the sense, the size of our muscles for manufacturing goods and services. I don't actually have a strategy. I think I listen a lot to classical music. Most of the great composers were not appreciated in their lifetime. And then people understood very much what they were doing. And I suspect that in my lifetime, I'm almost 70 now, in my lifetime I'm not expecting this to take on. But I know perfectly well that in 30 or 50 years, this is what people are going to be talking about in economics. I have no doubt about that. I've been teaching this stuff for 30, 40 years. I've never had a student take this basic information from me and not basically say, yeah, because it's so intuitive. It's very straightforward. It doesn't take all kinds of math. A lot of the math that's done in economics is obfuscates the problem. And a lot of it is BS. And so most of my students who take economics, you know, they pass the test, they might even get an A, but they say, well, it has no meaning to me. It's just stuff you study for the exam. Whereas this stuff, I understand it. I understand it when I have my breakfast. You understand it when you do the dishes. Because what is doing dishes about? You add energy with scrubbing, and you use hot water, which has more energy, which emulsifies the food particles. And if you're really smart, you leave the dishes in the sink overnight and let what's called Gibbs free energy, or approximately that, for the clean water, do the work for you. Clean water has high energy content, can do a lot of work because of the polarized hydrogen and oxygen molecules. So once you start thinking about energy, absolutely everything you do is about energy. Absolutely everything that moves in the world is about energy, and you better understand the energy. And the economic system, of course, is about moving stuff from raw materials into finished goods. So it's got to be about energy. And why economists? I'll give you a good example. There's something called a production function in economics, a Cobb-Douglas production function. This is one of many examples I could give you. So if you do a Cobb-Douglas production function in economics, you say the production of stuff, of goods and services, is a function of capital and labor. That's what they like, capital and labor. That's what the economist is. And you take this equation and look at the growth, for example, of the United States economy. A guy named Dennison wrote 3 books on this. And he is left with about half of the growth unexplained. And so what the economists would say, oh, well, we can't explain that because the increase in labor is only this much, the increase in capital is only this much, the increase in the economy is that much. We can only explain half of the growth. The rest must be due to technology, to this spark of human ingenuity. But my colleague, Rainer Kummel, puts energy into the equation, and not only does the residual disappear, in other words, technology has no meaning except through more energy, but energy is more powerful than either capital or labor. After the second book, I sent some data to Dennison showing him, hey, this is how it is. He wrote me back a very nice letter, and then he wrote his third book not even mentioning energy. So I don't know where these guys come from. They're out to lunch. They borrow an equation from physics back in 1880 or so, and they think they're doing real science. And even the way that they use this equation, something called Hamiltonians, violates the laws of thermodynamics. So any real scientist looks at what the economist does, and it's a joke.
It's got to be really frustrating.
I wouldn't let my freshmen get away with this. I used to publish in Science and Nature all the time, even this kind of stuff. And I can't do that anymore. But it's catching on. It's catching on. A lot of people, because it's so bloody simple and bloody obvious, and it's so intuitive. And I haven't heard anybody, and I say to any of your readers, if you think I'm wrong, I mean, you can go to my website, Google Charles Hall Energy, go right to my website, and you tell me what's wrong, and I'll answer you. And if you are right and I'm wrong, if I've done something wrong, then I will put it on my website. Well, net energy is you have to get energy to live. You're warm right now. You're using energy to maintain your physiological structure, your genetic structure. So you've got to get energy in order to do that. You do that by eating. And in our society, food is so abundant now because of fossil fuels that we eat too much. But for most of our evolutionary history, it's been probably fairly tough, at least around the whole year, to get enough energy to make it. So the first thing is you got to have energy to live. Energy is the ability to do work. It's a little bit, if you really dig in deep, it's harder to define energy than you think. But photons come in from the sun, and they got some punch. And green plants are able to capture that energy and pass it through food chains, and so it gets set down. And when you drive a car, if you drove a car here or took the bus, you're breaking you're oxidizing those bonds that were put down 100 million years ago by phytoplankton, by little plants. And that's the oil that we do today. So you're just running on the sun. How do I explain it to Wall Street? Well, I'd go to my book and I'd look on nation. Here's the growth of the global economy and the growth of energy use. That's mostly coal, gas, and oil. Little tiny bit at the top is solar. All right, so what do I say to somebody at Wall Street? Well, if we plotted the Dow Jones Industrial Average for 100 years here, correcting for inflation, it's just prices, you got to correct for inflation. And we also plotted the use of energy in the industrial society. And what we have is that they both have the same slope. They are going up at the same rate, although there's a lot of wiggles in the Wall Street, in the Dow Jones, it always comes back to approximately what the energy is. So I'm guessing it's, I would make a guess that the Dow Jones is probably not going to grow a whole lot going into the future because we're not exploiting a lot more energy. And the energy that we're getting is costing us more. If you're going to burn oil, you got to find it. And this graph here shows that we found most of our oil back in the 1930s to 1960s, and that we haven't found as much oil as we've been using. The dark line is how much oil we've been using. And we've been using 2 to 3 barrels, 2 to 4 barrels of oil every year for each barrel of oil we find. So we know that we're using up the oil that we found in the past. We've got to change that graph dramatically, and there's no evidence. Even this year, there's no evidence that basically that graph is changing. What kind of society do you want? So I wrote a paper on this. I can send you the paper if you want, but let me give you the full answer. If you're on an island in the ocean and your only energy comes from one oil well, and if you get an EROEI of 1.1 for 1, that's about what we get with alcohol fuel maybe from corn. If you have 1.1 for 1, you can pump the oil out of the ground and put it in a tank and look at it. If you have a 1.2 to 1, you can pump it out of the ground, put it in a tank, refine it and put it in a tank and look at it. 1.3 to 1, then pump it out and refine it and ship it to where you want to use it and look at it. You can't use it. If you want to drive a truck, and this is including the energy to make and maintain the truck and the energy to make and maintain the roads and bridges and so forth, then you've got to have at least 3 to 1. But you can't put anything in the truck. So if you want to put something in the truck like grain, so you got to grow the grain and so forth, that might cost you 5 to 1, to do that. And so that includes the depreciation of the truck, but if you want to include the depreciation of the oil worker, the farmer, the guy who maintains the bridges and everything, then you've got to have something higher. We haven't done real precise calculations on it, but something like 7 to 1 if you want to educate the kids, 8 or 9. Oh, so if you're going to include the families to have you got to deal with the depreciation of the families to replace the workers. So that kicks it up to, where are we, 7 or 8 to 1. If you want to educate the kids, 8 or 9 to 1. You want to send them to McGill, maybe 11 or 12 to 1. And if you want to, if you want medical care, 13, 14 to 1. You want a symphony, 15, 16 to 1, and so forth. So, what do you want? And who's going to get it? So we think these issues bring a lot of focus on the issue of how do we slice the pie, because it looks to us in much of the Western society the pie ain't going to get much bigger. Well, the best we know is from Cuba, because Russia cut off the oil to Cuba in 1988, and the society was completely transformed. And the food disappeared from the supermarkets in a week. The average Cuban lost 20 pounds. That would probably be good. But it changed. They were very good about this. And my colleague Megan Quinn has made a movie on how they dealt with it. They understood what was going on. I mean, you'd have problems. You'd live in a skyscraper and the elevator would only run half an hour a day. In Japan, they're dealing with this now because they've cut off all the nukes, and I understand that you go into a shop and they just have little tiny lights above instead of all of these big fluorescent lights. So we have some examples. I was walking through the streets of Montreal with my wife this morning and said, how in the world would you run this city without oil? Everywhere we looked, everything, collecting the garbage, you know, and bringing in the food, and people going to work, and the buses going here and there, and elevators going up and down in the building, and everything. This is all based on cheap energy. How long is this going to last? How would you have a city like this without cheap oil? And we don't know. I mean, could you do it with horses? Well, we used to, but there was only a tenth as many people then. So behind all of this, you got so many more people, and this enormous increase in the availability of fossil fuels has allowed this enormous increase in population. Anybody who studies that is black and white. Bill Reese said that this morning, and I said it too. So this means we got to start talking about things that we haven't been talking about if we care. And I don't think we're going to do it. So I think it's going to be a very bumpy future.